Perfect. Okay. Hey, everyone.
Perfect.
Today we are going to hear a talk from Nelson Filipe Costa, who is a PhD candidate. Is this the technical wording, right? PhD candidate at Concordia, supervised by Leila Kosem. So I'm sure this is going to be a very fun talk that we all find very interesting. Nelson, please.
Thank you for the presentation. Yes, I'm a PhD student. I don't know what the appropriate term is. I'm graduating in October, and in this presentation, I'm going to present the last bulk of my research, which is on multilingual and multilabel implicit discourse relation recognition. From talking with Calvin at the beginning, I understand some of you are not from NLP, so before I delve into the details of my research, I'll give a brief presentation on what Discourse is, also present the framework that I'll be using and the corpora that I'll be using. And then on sections 3 and 4, I'll present my actual research. So let's start with introduction. What is Discourse? So Discourse is this linguistic glue that holds text coherent. So when we are reading a text, ideas don't appear in isolation. They are usually connected to each other. And Discourse is the field of NLP that studies how these ideas are connected. So if you look at this example here, we have two sentences, two ideas. The lights flickered, the power went out, and we understand that there's an implicit relation between them. They don't appear in isolation. We can understand that the lights flickered because the power went out, in which case there is a causal relation between the two ideas, or that the lights flickered and then the power went out, in which case we have a temporal relation. So this is what this course tries to do. It tries to model how these relations keep text coherent. But if you want a more formal definition, I'll refer to the Daniel Jurafsky and James H. Martin Speech and Language Processing book that says that language does not normally consist of isolated and related sentences, but instead of collocated, structured, coherent groups of sentences. We refer to such a coherent structured group of sentences as a discourse. So this is a brief overview of discourse. And why is discourse important? It's used across a lot of downstream NLP application tasks, such as text summarization. And in this case, discourse helps system understand how sentences and ideas are logically connected, leading to better content selection and coherence in summaries. Dialogue and conversational agents. Discourse improves the coherence and appropriateness of chatbot responses by modeling how uteruses relate. And finally, news and media analysis. Discourse helps for analyze bias, framing, and argumentative structure in news articles or opinion pieces. So these are some of the downstream applications of discourse across different NLP fields. But what are the challenges that we face in the discourse community? So over the year, different frameworks have been proposed to model discourse. However, there's not one, up until today, there's no consensual discourse framework. So we have different research communities in NLP following different research discourse frameworks, which makes it hard to have cross-lingual applications across these different frameworks and even leverage all the resources that we have available. So that's one of the challenges that we have. Second challenge comes at the annotation of implicit discourse relations. So even if we agree on the discourse framework, we pick a discourse framework, and we start annotating this text following this discourse framework, there will be annotation disagreement when it comes to specifically implicit discourse relations, as they are more ambiguous to annotate. And then a common problem across NLP is that most resources in discourse analysis only exist in the English language. So this leads to biased models. And then this leads to the overall problem that motivates my thesis is we want our models to understand discourse correctly, yet we humans can't even agree on what correctly looks like. So this is the main motivation for my thesis. I want to converge divergent perspectives on discourse coherence to achieve a more explainable and comprehensible understanding of its underlying mechanisms. I broke my main research goal into three specific research goals. First is try to map relations between two of the most widely used discourse frameworks, the PDTB and the RST. The second one is try to build a model that's able to understand ambiguity in implicit discourse relations and model this with and model it as a multi-label task, and then extend our multi-label model to the multilingual setting where we incorporate other languages. In this presentation, I won't cover research question number 1. I'll just focus on the last 2, which were the last bulk of the research that I've done. So I'll present research question number 2 and research question number 3. But first, a quick overlook of the theoretical background. We need to follow this presentation. As I said, there's multiple discourse frameworks. 2 of the most widely used are the RST and the PDTB. Each of these frameworks have corpora annotated following its guidelines. In this work, I will only touch PDTB because it's the one that I've used for research question number 2 and number 3. So the PDTB has multiple, but I will talk about 3 discourse corpora: the PDTB3, the DiscoGem1, and the DiscoGem2. But before I delve into the corpora, let me present what the PDTB framework is. So the PDTB framework tries to model discourse around the idea of discourse connectives. And discoursive connectives are semantic cues, such as in this example, the word because. The striker played really well because he was able to score a hat trick. The word because is telling us there's a relation between one idea and the other, a causal relation. So the PDTB framework is anchored around these discourse connectives, and the annotators following this framework will go through a text, look for these discourse connectives, and then once they find them, they will look for the ideas that these connectives are trying to link, which are called the arguments. So in this case, argument 1 would be the striker played really well, and argument 2 is he was able to score a hat trick, and the discourse connective is linking these 2 ideas. So this is the most common example that we see in text, and it's called an explicit relation because we have the explicit discourse connective linking the ideas. But sometimes we still have the discourse relation without the connective. So if we were to remove the word because, we have the striker played really well, he was able to score a hat trick. There's no explicit discourse connective, yet we are still understanding that there's a causal relation between the 2 ideas, in which case this is an implicit relation. There are other discourse relations, but these are by far the 2 most common ones and the ones that are relevant for my work. Once we find the discourse relations, either explicit or implicit, we then annotate them for their sense. So in our previous example, the word because is a causal relation, so it would be somewhere here. And in the PDB framework, this should be a single table, but in order to fit it in the slide, I broke it into 2. In the PDB framework, senses are organized according to 3 levels. There's 4 main senses at level 1, which are temporal, contingency, comparison, and expansion. These are like the umbrella terms, which are then more finely grained defined at level 2. And some level 2 senses even have a level 3 finer definition. So for example, if we consider that we have a temporal relation between 2 arguments, then at level 2 we'll see if it's a synchronous relation, if both arguments are happening at the same time, or if you have an asynchronous relationship, if both arguments are not happening at the same time. And if you have an asynchronous relationship, is the argument 1 happening before argument 2, or is argument 1 happening after argument 2? So an annotator following the PDTB framework will first annotate the text for implicit and explicit discourse relations, and then for its sense. And following the PDTB framework, we have the PDTB 3.0 corpus, currently on the 3rd iteration. And this corpus consists of over 53,000 discourse relations. As I said, the vast majority are explicit and implicit relations. They make up almost 86% of the corpus. But there are other relations that are a bit more nuanced and which I won't cover, which are the alt-lex C, entity relation, hypophora, and no-rel. So in this work, I'll mostly talk about explicit and implicit relation, and I'll pay special attention to implicit relations, which are the ones that are more ambiguous because we don't have the explicit connective giving us the semantical cue as to what relation we have between the 2 arguments. And the PDTB corpus was annotated, as most corpora in the discourse world are, with a single sense. And I say mostly because there's 4.9% of the implicit relations where the expert annotators couldn't agree on a single sense, so they were annotated with two senses. And then another corpus that came out recently in 2022 is the DiscoGem corpus that came to defy this idea that relations should have a single sense. And what they proposed is a multi-label corpus. They collected 6,800 implicit discourse relations following the PDTB framework, but instead of having a group of expert linguists agreeing on a single sense per relation, what they did is they spread this task among lay people and asked each person to find the sense that they found more appropriate for each implicit discourse relation. And for each implicit discourse relation, they collected at least 10 different annotations, which then they averaged to have a distribution of the possible senses per relation. So let's say that for an implicit discourse relation, we'd have 7 annotators saying it's sense A and 3 saying it's sense B. Then they would say that this relation is 17% sense A and 30% sense B, thus keeping a multi-label sense annotation. And they collected implicit discourse relations from different genres, from political texts, literature texts, Wikipedia texts, and also 302 relations directly from the PDTB corpus. And then last summer, 2024, the same authors extended their work to different languages. So they picked their political text, their literature text, and they found parallel translations of the same discourse relations in different languages, in German, French, and Czech, and repeated the annotation procedure with annotators from these languages to have a discourse annotated corpus across all these 4 languages. So these are the 3 corpora that I will be using in my work. And the first thing I tried to address in my research was the ambiguity of implicit discourse relations. How can we capture multiple labels per discourse relation? And for this, I'll mostly use the DiscoGem 1 corpus and a little bit of the PDTB 3.0 corpus. And to address this research, I'm going to use the results that I've published at Cody last year and that I'll be presenting at SIGDIAL next month. So let me first motivate why the implicit discourse relation recognition task is an ambiguous task. Maybe this is not the best example that I could come up with, but it feels very personal right now. So let's consider this example. He loves running marathons, he is injured. There's no explicit discourse connective telling us what's the relationship between these 2 ideas. So one is free to interpret them as, for example, he loves running marathons and that's why he is injured, in which case we would have at level 1 contingency, level 2 cause, level 3 result implicit discourse sense for this implicit relation. Or we could interpret this as he loves running marathons, however, he is injured, which would have a completely different sense annotation. So understanding implicit discourse relations really depends on the context that you provide and the personal background of the person reading it. So it's an ambiguous task. It's open to different interpretations. In a traditional task, so up until today, all the work that has been done on IDRR would try to find a single label that would best define this implicit relation, which in this case could be contingency cause result. But what we are trying to do in this work is defy this idea and say that instead of just trying to pick the one sense we deem more appropriate, why not keep it both senses? So these are random numbers, but why not keep it as 60% contingency cause result relation and also 40% comparison concession and argument 2 as denier relation. So this is what we're trying to advocate in our work, is this ambiguity in implicit discourse relation recognition. As I said, previous work has always done this as a single label task, and these are the last works that have been done on IDRR. And as you can see over the past year, they have plateaued both at level 1 and level 2. Also, it's important to note that previous work never tried to do level 3 classification because it's already hard to do level 2, so level 3 is even harder, so they just usually dismiss it. In our work, we try to do level 3. And as you can see, results plateaued around the 71 value, F1 score for level 1, and around the 57 for level 2. And we argue this is because of their view that there should be only one single label, which it's a bit can be a bit narrow-minded. So what we propose is a classification model that will simultaneously predict the three level senses, so level 1, level 2, and level 3. And instead of predicting just one sense, it will predict the probability distribution of all senses on each level. And to measure our performance, we'll use the Jensen-Shannon distance in the multi-label setting. But because we're the first one to do this multi-label approach, and we want to somehow benchmark with previous work, we'll adapt our model as well to the traditional single label scenario, in which case we'll add a pooling layer at the end of each classification head to extract the sense which has the higher probability as our single label prediction. And in this case, we'll use the traditional weighted F1 score to measure our performance. And the loss of our multitask model is calculated as the equal sum of all the losses of each head. In this work, we consider different loss functions to see how they affect the multi-label task. So we consider a cross entropy loss function, the mean absolute error, mean squared error, and the Huber loss function with 2 delta values. And we also evaluated different pre-trained language models as the encoder of our classification model. So for each pre-trained language model, BERT, DistilBERT, RoBERT, and DistilRoBERT, we explored all loss functions, and what we found is that the mean absolute error in the multi-label setting, so the first 3 columns, leads to the better results across all the pre-trained language models. Maybe I should clarify, if you're not familiar with the Jensen-Shannon distance, here best is usually, it means lower results because this is a entropy measurement, so the lower the better. And what we see across all pre-trained language models is that in the multi-label setting, the mean absolute error always leads to the best results. However, in the single label setting, where we are evaluating with the F1 score, we found that the cross entropy loss function, which was usually used in literature under this setting, led to the best results. So in training our model for in the multi-label setting, we'll use the mean absolute error. And if we are doing single label IDRR, we'll use the cross entropy loss function. And then with this in mind, we explore different learning rates, which explored a few decay functions to fine-tune our models. And in the multi-label scenario with the mean absolute error, we found that the cosine annealing loss decay function, the learning rate of 1 to the power of -5, led to the best results. And in the single label setting, we opted for the linear decay function with a learning rate of 5 to the power -6 for the training of our model. And doing this, we evaluated our model on DiscoGem1. We evaluated our model in the multi-label setting and in the single label setting. As I said, we are the first one to conduct IDRR on the multi-label setting, so we had no previous work to compare ours against. So we came up with our own baseline, which tries to replicate the annotator procedure of the DiscoGem corpus, which is we have 10 individual classifiers trying to find a single label, and then we average these single labels in a distribution. And as we can see, our models training with both mean absolute error and the cross entropy surpass the baseline by considerably. And then in the single label setting, we could compare our work with our previous work, the one that we presented last year at Cody, at the level 3, and also with the work of Young et al. That these are the authors of DiscoGem that also came up with their own model in a single label setting, but only for level 2. And we see that our work considerably surpasses their performance. And also the baseline. At level 3, our model with cross entropy is at par with the model that we presented last year at Cody, with the difference that our model does 3 levels predictions at the same time. Our most recent model does 3 level prediction at the same time, and this previous model that we had only did 1 level prediction. Also note that our baseline method and the method proposed by Young et al. Are very similar, which attests for the reliability of our baseline benchmark. And then we were wondering, since the DiscoGem was annotated following the PDTB framework, could there be a transfer learning potential between a model trained exclusively on the DiscoGem onto the PDTB? So what we did was we picked our single label model trained on the DiscoGem, and without fine-tuning it on the PDTB tree, we evaluated it on 3 of the test sets used in literature to see if there could be transfer learning. And unfortunately, we see that there's still work to do in this setting. If we compare our results against previous state-of-the-art models, we see that our model that was not pre-trained on the PDTB tree still lags a bit behind the state-of-the-art, which means that blind direct transfer learning does not work, but the results aren't so bad either that should exclude any future research in this area. Then we did some more digging and we looked at the percents performance of our model. So these are F1 scores on individual senses. So at level 1, temporal contingency comparison expansion, and at level 2, synchronous, asynchronous, and so on. This also shows the same results, but as contingency tables. And then what's probably more interesting is the sense coherence across levels. So as we saw, the way the PDTB framework defines senses is through that hierarchy of level 1, level 2, level 3. So what we're interested in seeing is if our multitask model is coherent in its prediction. So if at level 1 it predicts a temporal relation, does its level 2 prediction make sense or does it not? So if it predicts at level 2 asynchronous and asynchronous, then it makes sense, it's coherent. But if it predicts at level 1 a temporal relation and then at level 2 a cause relation, then it's not coherent at all. And what we found is that our model, without us explicitly defining this sense hierarchy, is usually, it's for the most part capable of predicting coherent predictions, with the exception of the expansion level 1 level. If we look at level 2, like the results are pretty good, 97, 100%, and so on. Some of the senses do not exist in the DiscoGem, so we could not predict them, but for the one that existed, we achieved good performance. So this is our model for our proposed model for the first model in multi-label IDRR. We established the first benchmark on multi-label IDRR using DiscoGem 1. We also adapted our multi-label model to the traditional single-label IDRR setting and compared it to previous work. And we presented the first analysis on the potential of transfer learning between the DiscoGem 1 and the PDTB3 corpora on single-label IDRR. And then we wanted to extend this work to the multilingual setting. And to do so, we'll mostly leverage the DiscoGem 2 corpus and also the DiscoGem 1 corpus. And this work is based, the work that I'm going to present here is based on another paper that I'll be presenting next month at CDL. So here we try to improve our previous model and we try to develop a hierarchical, that we call H-arch classification model, where we try to explicitly model the sense hierarchy in the PDTB framework, in the sense that the prediction of our classification at level 1 will be cascaded to the prediction of our classification at level 2, and the prediction of our classification at level 3 will be informed by both the prediction of the classification at level 1 and the classification at level 2. And to do so, we have these weighted sums that are also based on trainable parameters by the model, alpha and beta, that will learn how much weight each classification head should pay to the, how much importance each classification head should pay to the previous classification heads. We also compare our H-Arch model to LLMs in a few shot prompting setting. In this case, we explore different prompts, and we ended up going with this role-playing prompt setting where we have a system message. We provide a few examples from the Discourse gem that have been annotated by the Discourse gem, and ask the model to generate a prediction as if he was an annotator of the Discourse gem corpus, and we compare it to our H-Arch model. And here are our results using both the prompt setting, which are in this slightly dark grade, the last two rows in the English and multilingual setting. Sorry, let me break this table better. So here at the top, we have different models trained and tested only in the English language. And at the bottom, we have different models trained and tested on all languages simultaneously. The last two rows of each part correspond to our prompting methodology using large language model. We use GPT-4 and Llama-4, the two most recent LLMs. And in our H-Arch model, similar to what we did before, we explore different pre-trained language models. We experimented with Roberta, with Modern BERT, and with XLM Roberta for the English setting. And in the multilingual setting, we explored XLM Roberta, eRobert, and FLAN T5. In the English setting, we also compared against our previous model from the previous research question in the English language. And what we found is that in the English language, the Roberta-backed model achieved the best results, and in the multilingual setting, the XLM Roberta model achieved the best results. What we found surprising as well was that not so surprising, but interesting, is that our fine-tuned models outperformed the large language models across all levels, across all languages. So based on this finding, we went back to Discourse Gem 1 and we applied our Roberta-backed H-Arch model on Discourse Gem 1, similar to what we did before. And we found that by explicitly cascading the information from level 1 to level 2, and from level 1, level 2 to level 3, we achieved better results at level 2 and level 3. At level 1, we didn't see a change in performance because everything is the same. There's no cascading into level 1. So this shows that explicitly cascading information does lead to better results, a good sanity check. And then we were interested to see how much importance does level 2 see from level 1, and how much importance does level 1 and level 2 pay in the prediction level 3. So we saw the values of our alpha and beta parameters, and we saw that the prediction at level 2, by 51% of the prediction of level 2 is based on the prediction of level 1, and 26% of the prediction at level 3 is based on level 1, and also 26% of the prediction of level 3 is based on level 2, with the rest of the percentages coming from the encoded text that's inputted to the model. We then did more experiments with all the different languages in a multilingual setting. So this is a big table, but pretty much we separated this into all languages simultaneously, only the English language, only the German language, only the French language, only the Czech language. In the multilingual setting, we used XLM Roberta, the one that achieves better performance, and we kept our LLMs in the prompting setting. English as well, we kept Roberta and as well XLM Roberta. And for German and French and Czech, we only used XLM Roberta. And we saw that across all languages, across all levels, our fine-tuned models always outperformed the LLMs in a few-shot prompting setting. Another thing we wanted to evaluate that we didn't evaluate in our previous model, in our previous research question, is how much of an advantage it is to have our model predicted 3 3 levels simultaneously as a multitask, in a multitask setting, over having single models predicting each level individually. So in the English setting, this is our Arch model that predicts the three levels simultaneously. And here we have the same model, but predicting only one sense at a time. And we see that in the English setting and in the multilingual setting, having the model predict 3 sense levels simultaneously leads to better results. Why? Because the information because the way that the PDTB framework is structured, there's an implied relation between level 1, level 2, and level 3. And by doing a multitask prediction, we are able to encode this relation between the different levels, which leads to better results. Also saves us a lot of computational times, as we can see on this last column. So as a summary for this last research question, we propose a first multilingual and multilabel model for IDRR. In the English setting only, using Discourse Gem 1, we improved our previous state-of-the-art results on the multilabel setting. On the multilabel setting. On the multilingual setting, we established the first benchmark on multilabel IDRR using Discourse Gem 2.0. And we also showed that our fine-tuned Arch model outperforms LLMs in the context of IDRR with few-shot prompting. So as a conclusion, research question number 2, can we build multilabel IDRR models capable of distinguishing between ambiguous implicit senses? The answer is yes, and in doing so, we established a first benchmark on multilabel IDRR. We also adapted our model to the traditional single-label IDRR to compare it to previous work, and we provided the first study on the potential of transfer learning between Discourse Gem 1 and PTB3 corpora on single-label IDRR. Then for our research question number 3, can we build a multilingual and multilabel model? The answer is yes, and our hierarchical model even improved on our previous model in the English setting alone using Discourse Gem 1. And we provide a first benchmark on multilingual and multilabel IDRR. And we show that our fine-tuned model still outperforms LLMs in the context of IDRR with few-shot prompting. There's still a few research directions I'm not sure I'll be able to explore since I'm graduating in October, but it's open for future work, which is exploring graph neural networks to address the multilabel IDRR problem. And in the context of transfer learning between the Discourse Gem and PDTB, could we further fine-tune our Discourse Gem models on the PDTB data using also the metadata from single-label IDRR? And instead of just prompting LLMs, try fine-tuning LLMs using low-rank adaptation methods called, more commonly known as LoRa, for multilabel IDRR. And this is it.
Nelson, thank you much for this presentation and taking us through some of the work that you've been doing recently. I'm sure.
My pleasure.
So